Imagine this. We usually think time never stops or slows down for anyone. It keeps moving forward, not waiting for anything or anyone. But what if I told you that might not be entirely true? Enter Einstein's special relativity theory, which suggests that time doesn't behave the same way for everyone. In simple terms, Einstein's theory is based on two key ideas. First, it says that the laws of physics are the same for everyone, no matter where you are or how fast you're moving. Let's imagine you're on a train moving at a steady speed, and your friend is standing on a platform. From your friend's perspective, they're at rest, while you appear to be moving forward. But from your viewpoint inside the moving train, you feel at rest, and it seems like the world outside is moving towards you. Think of it like this: if the train windows are closed, and there's no external reference point, you might believe you're at rest. The laws of physics work the same way for both you and your friend, so both perspectives, one moving, one stationary, can be considered equally valid. To simplify, let's consider a mosquito inside a flying plane. Picture it perched on the back seat, desiring to fly to the pilot's room. If the laws of physics weren't consistent for a moving plane, the mosquito would need to travel faster than the flight speed. However, that's not the case, and the mosquito perceives itself at rest in the moving plane. Therefore, its usual effort is sufficient to reach the pilot's room. Now, let's shift back to the train scenario. Imagine you're in a moving train while your friend is on the platform. Anything your friend does on the platform, you can do in the moving train. However, the speed isn't uniform for all observers. Suppose the train maintains a constant speed of 100 kilometers per hour, and you throw a ball at 20 kilometers per hour. From your perspective inside the train, the ball seems to be traveling at 20 kilometers per hour since you're at rest. Contrastingly, from your friend's viewpoint on the platform, the ball appears to zip by at a whopping 120 kilometers per hour. Let's introduce another friend running toward your train at 10 kilometers per hour. If this friend measures the ball's speed, they would perceive it to be 130 kilometers per hour. Why does the same moving object display different speeds? It's because speed is relative, varying based on the observer's perspective. Different observers can gauge different speeds for the same moving object. Let's talk about special relativity. Special relativity introduces another fundamental principle, asserting that the speed of light remains consistent for all observers. This unchanging speed is constant, maintaining the same value across various frames of reference. Let's explore this through a straightforward example. Imagine you and your friend standing opposite each other, with your friend holding a flashlight. If you were to measure the speed of light quickly, you'd find it around 300,000 kilometers per second. No surprises so far, as both of you are at rest. However, envision yourself running toward your friend at an extraordinary speed of 10,000 kilometers per second. And even then, the measured speed of light remains at 300,000 kilometers per second instead of showing any increase to 310,000 kilometers per second. This underscores the constant nature of the speed of light, unaffected by an observer's state of motion. To uphold this constancy of the speed of light, space and time undergo peculiar features. Now, what about time itself? Despite our current understanding being somewhat basic, we collectively agree that all clocks tick at the same rate, measuring the duration of events and synchronizing our daily experiences. Contrary to this consensus, the constant nature of light challenges these notions. Consider two nations, Nation A and Nation B, eager to sign an agreement simultaneously. The challenge lies in achieving this synchronization. Their chosen procedure involves the leaders of both nations sitting at opposite sides of a table, with a light bulb positioned in the middle. As the light is switched on, reaching both leaders' eyes simultaneously, they sign the agreement simultaneously. The leaders strategically position themselves at the same distance from the light bulb, ensuring that, due to the constant speed of light, the illumination reaches both at precisely the same moment. This visual representation ensures a harmonious signing of the agreement, bringing contentment to all involved. After a few months, the leaders decided to sign another agreement, but this time they wanted to do things differently. Despite having many different opinions, both leaders shared a strong passion for trains. So, they recreated the same scenario, but this time on a moving train. As the train moved, the light flashed, reaching both leaders simultaneously. They happily signed the agreement, and everyone in the train was pleased with the result. However, trouble arose among the people on the platform. Those from Nation B complained that the leader of Nation A signed the agreement first. How did they reach this conclusion? If we look at the event again, the train is moving, and the light flashes. Leader A is moving towards the flash, while Leader B is moving away. This made it seem like the flash reached Leader A first because he was approaching it. They knew that light always travels at a constant speed. Leader B, moving away from the flash, took longer to be reached compared to Leader A. From the platform perspective, it seemed like both leaders didn't sign at the same moment. But from the leader's perspective inside the moving train, they claimed they signed at the same moment. We already know that when an object moves at a constant speed from that perspective, it can claim to be at rest. Now, let's shift from the platform perspective and simplify the event. Imagine drawing a line when the flash occurs and another when it reaches Leader A and Leader B. It's clear that the flash reaching Leader B had to travel a longer distance compared to Leader A. Light always travels at the same speed, so if it has to travel a greater distance, it takes a longer time. So, who is right here? The leaders inside the train or the people watching from outside? The reality is both are correct. What does this tell us? The constant speed of light means that events take place at the same time, even though one group perceives a time difference that the other group doesn't notice. It's not an optical illusion, it's reality. What happened from one person's perspective doesn't happen at the same moment as it does from another person's perspective if they are in relative motion. Okay, let's talk about time dilation. Imagine a clock. There are many types of clocks, but we'll use a light clock to explain time dilation easily. The light clock is simple, just like any other clock. It has two mirrors and a light ball bouncing between them. Think of the light ball as light. Each time the light ball goes up and down, like a tick-tock, it counts as 1 second. Now, let's take another light clock. We'll keep one clock still and put another one in motion. The moving clock, we can see the light ball moving diagonally. The counts on both clocks are different. Why is that? Look at the path of the moving clock, it's a double diagonal. One full up and down movement takes longer compared to a still clock. This happens because light needs to travel a longer distance. However, the speed of light is constant, always the same for everyone. In a moving clock, each tick-tock happens at a slower rate. Slower tick-tocks mean time runs slowly. This slowing of time is only noticeable for someone watching the event from the outside. From our point of view, time runs slowly for the moving clock. But for someone inside the clock, they don't feel any time difference. This is because they move along with the light clock, so they can't feel the diagonal path of the light ball. As we know, when an object moves at a constant speed, it can act as if it's at rest. So, when an object is in motion, its time slows down. But you might wonder, why don't we see time dilation in our everyday lives? Let's check out the time dilation formula. gamma equals 1/sqrt1b/c2. Now, imagine two clocks, one on Earth and another on a rocket in space. Let's make the rocket move at 10% of the speed of light. At this speed, it's hard to see the time difference, although there is a small one. Now, increase the rocket speed to 70% of the speed of light, and we can really notice the time difference. The time on the rocket is less than what we see from Earth. Move the rocket to 98% of the speed of light, and we'll experience a significant difference in time. From our viewpoint on Earth, the clock on the moving object ticks very slowly. Therefore, time dilation happens universally. However, it becomes noticeable mainly when moving close to the speed of light. At everyday speeds, time dilation still occurs, but it has a very tiny effect. To understand better, let's consider another example. Picture a light clock on a moving train. If the train's velocity is 10% of the speed of light, there's some time difference, but it's not very noticeable. It seems like the light ball is following a straight path up and down. Now, increase the velocity to 70% of the speed of light, and you'll clearly see a diagonal path of the light ball. If the train moves extremely close to the speed of light at 99.99%, there's a significant difference in the diagonal path. In this case, the light ball doesn't make a single tick, while a stationary clock continues its normal tick-tocks. Up to now, everything seems theoretical and formula-based. So, we can't conclusively say that time dilation occurs when an object is in motion. Are there any real-life experiments proving it? Absolutely. Let's consider two simple experiments. The first one, conducted in 1971 by scientists Hayfele and Keating, used two synchronized atomic clocks, one stationary and the other on a plane flying around the world. When the plane landed, they compared the two clocks and found a 60 nanosecond difference, exactly as predicted by Einstein. This experiment directly confirmed that time on moving clocks ticks at a different rate than stationary ones. Scientists did an experiment with muons, which are like electrons but last only 2.2 times 10 to the power of -6 seconds before breaking apart. Muons sometimes take a bit longer to break apart when they are in motion, but their own disintegration time stays the same. Our perception makes it seem like muons take longer to break apart when they're moving, proving that time slows down when an object is in motion. Imagine you and your friend are the same age, and you both don't know about special relativity. You leave your friend on Earth and travel in a rocket near the speed of light for 6 months. When you return, you say only 6 months passed for you, but your friend tells you 40 years have passed on Earth. This is how time dilation works, showing the beauty of special relativity. Einstein, with his genius, figured this out using the constant speed of light. There's another type of time dilation with gravity, but we'll explore that in another video.